Welcome to the EC Game Changer Seminar online series. This time we started with a new series. Actually, last time we started already with a new series of 10 talks. And this new series is on captivating cosmology from the Big Bang to tomorrow. And today we are, of course, happy to listen to Will Kinney about the cosmic inflation and the beginning of the universe. Or an infinite of words. It's also written in the title. So my name is Maurizio Falanga. I am your host and Astronomy and Astrophysics Director at the International Space Science Institute. I invite, of course, all of you also to take a look at our webpage to learn more about EC, and especially how also to use EC as a tool or as an institute for your own scientific activities. So back to the talk. At the end of the talk, you have two possibilities to ask questions. One is you can raise your hand and we will unmute your microphone, or you can write the questions also during the talk or at the end in the chat, and then we will read the questions to Will. About Will, first of all, thank you so much that you accepted our invitation in this new adventure in cosmology, at least for EC. And Will is a professor in the Department of Physics at the University of Buffalo, where he has been of faculty since 2003. And before, he received his Bachelor of Arts from Princeton University and the PhD from the University of Colorado in Boulder. He has worked as a research associate at the Fermi National Accelerator Laboratory at the University of Florida, Columbia, and held visiting position at Yale University and several positions or visits also in Europe. His research is focused on the physics of the very early universe, including inflationary cosmology, the cosmic microwave background, dark matter, and dark energy. And he has also received several awards, including in teaching. So thank you once more for accepting our invitation, and we are all eager to listen to your talk. So let's say the screen, it's yours.
Thanks, Maurizio. I appreciate the invitation, and thanks to the audience for showing up. So I am going to talk to you today about the beginning of the world, the ultimate origin of the universe, which is something that I think human beings have been interested in for as long as we've been human beings, that we have always, it's a constant of human culture that we tell ourselves stories about our origins. And of course, it's only been, sort of recently with the advent of scientific inquiry and cosmology that we've been able to look at this question scientifically and really come up with definite answers based on a scientific understanding of the world to really begin to understand where the universe came from. And this is perhaps one of the most consequential developments of 20th century science, was the realization that the universe in fact had a beginning, that the universe has a finite age. And we've even measured that age to astonishing accuracy. So we know that the universe is, our universe, the one we live in anyway, is 13.8 billion years old with an uncertainty of only about 200 million years. And this is a triumph of modern astrophysics that we've been able to determine this. And I want to tell you a little bit about this story and about some of our more modern theories, in particular the theory of inflation, that places this beginning, this initial moment of the universe into a larger context and with, in many ways, quite surprising results. So let's go back to the ancient Greek philosopher Aristotle, whose conception of the universe, Aristotle's concept of physics, was one of hierarchy, and in particular that terrestrial objects and celestial objects really had completely different rules that describe them. And in particular, Aristotle's conception of the physics of terrestrial bodies, right, material things, was that motion was an unnatural state, right? And that everything tended to collect essentially at the bottom of the universe on the Earth, and that motion, anything in motion had to have a cause. And Aristotle, this led Aristotle to the concept of a first mover, a first cause to the universe. Since everything in motion must be moved by something, then anything that is in motion that motion had to have been caused by something else, and that cause had to have been caused by something. And he followed that chain back and postulated that there must have been some initial cause to the universe that created the motion in the world. And this led to the Ptolemaic system of cosmology, in which the Earth is essentially at the bottom of the universe, not in a privileged position in the sense that we were inferior, right? So that all of the material bodies in the universe collected at the bottom as sort of this drain pipe of the universe that was the Earth, and then above us is the perfect heavens. So the rules governing the motion of celestial bodies were completely different in this conception than the rules governing the physics that govern the bodies on Earth. We, in this sense, were very special. And this was something that was imported into, for example, later Christian theology with Thomas Aquinas's view that the universe was God-ordained and man-centered, right? So that we are in this special privileged position in the universe below these imperfect beings, below these perfect heavens, this hierarchical view of the world. Copernicus turned that on its head. Copernicus, in introducing his heliocentric cosmology, realized that this Aristotelian separation of the material bodies and ethereal bodies, that the non-universality, this hierarchy of the universe, needed to be destroyed. If, in fact, the Earth is orbiting around the sun, Copernicus realized necessarily that he had to introduce a concept of relativity. And relativity in its modern conception was first introduced by Copernicus, even prior to Galileo, where he wrote in his treatise De Revolutionibus that for every apparent change in respective position is due to motion of the object observed, or the observer, or an unequal change of both. So it was really Copernicus who created this sense of relative motion. And this biological conclusion requires a universality of physical law. In the Copernican system, in the heliocentric system, we live on just one of many planets that are orbiting around the sun. We have no special position. And this, in fact, is the Copernican principle, the idea that our position in the universe is in no way special. And that Copernican principle, this idea that our position in the cosmos is in some sense ordinary, then requires that all of the physical laws that govern our motion be universal physical laws. So Copernicus set us free, realized that we have always lived in the cosmos, and that the laws of physics we see here on Earth are not in any way special. And if they're not in any way special, then they apply in the rest of the universe as well. This idea of our ordinariness was taken to its logical extreme by the Renaissance philosopher Giordano Bruno, who wrote in 1584. Bruno realized that if you fully embrace a Copernican viewpoint on the universe, that means that not only is the Earth in some sense ordinary, but that means that there must be other suns, other Earths, other planets, other civilizations. And he wrote in 1584 that God is infinite, so his universe must be too. He is glorified not in one, but in countless suns, and not in a single Earth, a single world, but in 1,000,000, I say in an infinity of worlds. Bruno, in many ways, was hundreds of years ahead of his time. He realized that fully embracing the Copernican idea of our own ordinariness, of the fact that we're not special in any way, necessitated an infinite universe of which we are only one small piece. And that's reflected in modern cosmology and the idea of the Big Bang as the principle, what is now called the cosmological principle, which is that not only are we not in a special place in the universe, no place in the universe is special. And this is reflected mathematically in the assumption that the universe is homogeneous and isotropic. That is, that the universe of the Big Bang must have no center and no edge. Now, I think there is, even among scientists, but certainly among the public, there's a misconception about the Big Bang. People tend to imagine it as being an explosion, something that happened at some point in space where there was some cosmic egg that exploded outward and everything moved away from the central point of this explosion in space. And nothing could be further from the truth, because that in fact violates the cosmological principle, this Copernican idea that there is no special place in the universe. If no place is special, then the universe can have neither center nor circumference. This was actually, I'm actually quoting Copernicus at this point. And so this idea of an explosion taking part from some central point in space, the idea that the Big Bang happened at a place, violates this principle. So instead of thinking of the Big Bang as an explosion, instead I'd like you to imagine a grid of squares. So I can draw, as what I'm showing here on this slide, a grid of identical squares, and no point on this grid is special in any way. Each square is exactly the same as the others. Of course, if this is to have no center and no edge, it must extend infinitely. So I want you to imagine this grid of squares, which is finite on my screen, extending infinitely in all directions. We just have these an infinite grid of completely identical squares. This satisfies the cosmological principle. There is no center and no edge. Every point on this infinite grid of squares is the same as every other point. And in the real universe, of course, we generalize that to 3 dimensions. So you can imagine a grid of cubes. So how can the universe be expanding? This is one of the basic observations that dates back to Edwin Hubble in the 1920s, is he realized that all of the galaxies we see are moving away from us. And the further away the galaxy is, the faster it's moving away from us. So in order to imagine cosmological expansion, not as an explosion away from a point, but as the expansion of space itself, we will make each of these squares a little bit bigger. So as we scale these things, as these squares get larger and larger and larger, every point in the space is moving away from every other point in the space. And it's not hard to convince yourself that, in fact, it obeys Hubble's rule that the further away you are, the faster you're moving, because each square expands by the same amount. And so the further away you are, the more squares there are in between you and us. So as that expansion takes place, so the more two objects that are more distant from each other will be moving away from each other more quickly. This infinite grid of squares gets bigger and bigger and bigger. Everything moves away from everything else. But there is no center to this expansion. There is no special point at all. Everyone sees himself at rest, and everyone sees all of the rest of the universe moving away from them. And in this way, we can construct a universe that is growing larger, that's expanding, but still is not expanding from any particular point. Now, imagine turning the clock backward. If we look at our current expanding universe and we say what must have happened in the past, if we turn time around and look at the past, these grids, these squares would have gotten smaller and smaller and smaller. At every point, the grid of squares still extends off to infinity, but earlier in the universe, earlier in this history of this expanding space, all of these objects would have been closer and closer together. And when you plug this into Einstein's equations for gravity, if you plug a homogeneous and isotropic universe into the equations for general relativity, what you find is at some finite time in the past, all of these squares would go to 0 size. This is known as the initial singularity, or the moment of the Big Bang itself. And the point at which all of these squares shrink to 0 size and the universe shrinks to infinite density is known as a singularity. At this point, our understanding of the physics breaks down, and this, in the standard Big Bang model, is the moment of the Big Bang itself and the moment of the creation of the universe. And in fact, this moment of the Big Bang, if you still see this grid of squares extending infinitely in every direction, the Big Bang didn't happen at one place in the universe. It didn't happen at a point. It happened everywhere in an infinitely large space at once. The initial singularity, the boundary of our universe, the beginning of time, is a boundary in time, not a boundary in space. And at that moment, immediately at that boundary in time, at the beginning of the universe, an infinite homogeneous universe sprang into existence all at once. Similarly, if we look at the contents of our universe today and say what happened to all of the gas and dust. Our universe is composed primarily of hydrogen and helium. What happens when you have a universe full of all this stuff and you travel backward in time, you extrapolate backward into the earlier history of the universe? Well, everything would have been crammed together more tightly. The density of the universe was higher at early times and gradually got lower as the universe expanded. And if you take a gas of hydrogen and helium and make it denser and denser, if you push it together, what happens to it is it gets hot. So this picture of the early universe arising out of a process of expansion also means that the early universe must not only have been very dense, but it would have been very hot. The temperature of the universe was extremely high. And because of this, where the temperature of the very early universe was so high that the language that we need to use to describe the physics of what was going on in the universe at that time is the language of high energy physics, of particle physics. The gas would have been so hot that it would have consisted of a primordial soup of particles that were smashing into each other at very high speed. And in order to understand this, we need to use particle physics to understand our cosmic history. So I want to just give a brief outline of how this history looks, or a very brief tour of the entire history of the universe. And in order to do that, we need to populate our universe with stuff. And cosmologists divide the material in the universe up into three categories: matter, radiation, and vacuum. And these three things differ by how they behave under expansion. The first thing, matter, is if I imagine a box full of dust, material objects, hydrogen atoms, or particles of dark matter. We don't know what the dark matter is, but most physicists believe it consists of some sort of non-interacting particle. If I take that box and make it bigger, as the universe expands, my box and any box that contains this material will expand as well. This is called a co-moving box. So if I follow the material in my co-moving box, what I find is that as the universe expands, that material gets more dilute. It dilutes away with the proportional to the volume of the box. And this is the energy density of the matter in the universe is then proportional to 1 over the volume of any expanding box that is expanding along with the expansion of the universe. The second kind of stuff that we put in the universe, cosmologists call radiation. And this really would be any sort of relativistic particle, like a photon, neutrinos, for example, gravitational waves would all behave the same way. These things, as the box that they live in expands inside this co-moving box, they become more dilute. Their number density drops in the same way. For example, if I have a box of photons, the density of the photons would drop with the volume of the box in the same way as happened with matter. But another thing happens, which is that the wavelength of those photons, the wavelength of the light inside the box, will also stretch proportional to the expansion of the universe. This is called cosmological redshift. And if I have any wave propagating through the universe, as the universe expands, the wavelength of that wave will increase proportional to the expansion of the universe. So that means the effect of that is that radiation, things like photons, neutrinos, and so on, actually dilute more quickly in terms of their energy density than matter, things like hydrogen atoms or dark matter. And so if the universe, it consisted of mostly radiation at early times, that radiation dilutes away more quickly, and then at late times, matter would start to dominate. The third kind of material that we put in our universe, cosmologists call vacuum, which is essentially, you can think of it as an energy associated with empty space itself. And because this is an energy that's associated with empty space, it doesn't dilute at all. As the box gets bigger, the density of the energy inside the box stays the same. And so you actually end up with more energy in the box than you started with expansion. If this seems to violate conservation of energy, that's because it does. In fact, in general relativity, energy is conserved locally, but it is not conserved globally. That means we can create energy out of nothing inside this box. And this is what you see with the vacuum. If empty space itself has an energy, then if we create more space inside the box, there's more energy in the box at the end of the day than we started with. This is a very different behavior, of course, from matter and radiation. And so all three of these things combine into this great dance that occurs throughout cosmic history. So in fact, what we measure today is that if we measure the energy density of the universe, we find quite remarkably, actually, that regular stuff, atoms, the things that we're made of, only make up about 4% of the energy in the universe. Everything that we know about, all the hydrogen and helium, everything that makes us up, is only a tiny trace element to the real energy density of the universe, which is mostly dark energy, or the energy of vacuum. Energy of empty space itself makes up about 3/4 of the total energy density of the universe. Dark matter, which is yet to be identified, but we can see indirectly through its gravitational effect, adds up to about 23% of the energy density of the universe. And then atoms like hydrogen and helium are a small 4% on top of that. And too small to even see in this figure would be the radiation in the universe, the glow left over from the Big Bang called the cosmic microwave background that I'll talk about in a minute, is in fact a tiny, tiny trace now, but in the early universe, it actually would have been dominant. So here is a plot showing basically the entire history of the universe in the Big Bang sense, starting with very high temperature in very early time. So at about 10 to the minus 40, at an age of 10 to the minus 43 seconds, when the temperature would have been about 10 to the 32 Kelvin, our existing theories break down, and we would need a theory that combines quantum mechanics and gravity to describe it. As the universe expands, it cools. And so gradually, as the universe gets older and older, the temperature gets lower and lower. And the highest energy and temperature we have managed to probe in the lab is around 10 to the 16 Kelvin. This is energies comparable to what we are probing with particle accelerators like the Large Hadron Collider. All the way down to when the first elements form, when the cosmic soup cooled enough for protons and neutrons to form into nuclei, which happened when the universe was between 1 second and 3 minutes old. And down to the point, and all during this period, the universe would have been primarily dominated by radiation, things, relativistic species whose wavelength increases with the expansion of the universe. But when the universe cooled to about 10,000 Kelvin, it would have transitioned, the radiation dilutes more quickly than the matter, so it transitioned to a matter-dominated phase, after which, for example, stars formed and the first galaxies began to form. And then more recently, when the universe was at a temperature of about 5 Kelvin, about a few billion years ago, dark energy, the energy of this empty space would have come to dominate because it dilutes even less quickly than the matter and the radiation. So we go through 3 grand epochs of cosmic evolution, starting with radiation-dominated expansion, followed by matter-dominated expansion. And our universe today is just in the process of making the transition from matter domination into vacuum domination or domination by dark energy. And we today are at a point where the temperature of the universe is down to a nice cool 3 Kelvin or 3 degrees above absolute zero. So how do we probe this? How do we learn about the history of the universe? Archaeologists have to go back and dig up bones and look at indirect relics of the past. Cosmologists are lucky because we don't have to piece together our history from relics. We can see it directly. This is because telescopes are time machines. Looking out in space is looking back in time. So when I look at the sun, I am seeing the sun not as it is right now, but as it was 8 minutes ago, because the light takes 8 minutes to travel from the sun to us because of the finite speed of light. If I look from where we are out at the edge of the Milky Way galaxy, if we look at the black hole in the center of the Milky Way, we're not seeing it as it is today, but we're seeing it as it was about 30,000 years ago, because it takes light 30,000 years to travel from the center of the galaxy to where we are. So we are actually seeing backward into the past. If I look out at a galaxy that is, for example, 100 million light years away, I'm seeing it as it was 100 million years ago when dinosaurs were roaming the Earth. So looking out in space is looking back in time, and the further out we look, the further back in time we see. So in fact, we can see the entire history of the universe laid out before us. If we look out 1 billion light years, we can see the universe as it was 1 billion years ago. If we look out 10 billion light years, we can see the universe as it was 10 billion years ago. This has an additional effect, which means that because the universe has a finite age, we can only see out a finite distance. If the universe is 13.8 billion years old, we can only see out 13.8 billion light years. Actually, this is modified a little bit because of expansion, and the radius of the universe is more like about 40 billion light years because it's been expanding during this time. But the principle is the same. So imagine an observer immediately after the Big Bang looking out into the universe. Well, when the universe was 1 minute old, you could only see out 1 light minute. When the universe was 1,000 years old, you could only see out about 1,000 light years. And so this observer in this infinite expanding space would actually see themselves at the center of a finite bubble. And the further out in space you look, the further back in time you see. And the edge of that bubble, that observer would see him or herself sitting at the middle of a spherical bubble where the outside of that bubble is in fact the moment of the Big Bang itself. Light traveling from that radius would have started out immediately after the Big Bang. So what we actually see when we place ourselves in this infinite space is we see ourselves in a tiny finite bubble where the outside edge of that bubble is itself light that has traveled to us from the moment of the Big Bang. If we look in the sky, if we look out far enough, we could see the Big Bang itself. And no matter what direction we looked, we would see the Big Bang as it happened at that point. Then as the universe expands and grows older, our bubble expands outward. The amount of the universe we can see gets larger and larger and larger. So in this diagram, these two observers would be separated from each other. The first observer could not see the second one. But gradually, as the universe expanded and this observer's horizon, this finite distance that you can see out, got bigger and bigger, then these observers would see each other later on. So because of the finite age of the universe and the finite speed of light, we see ourselves inside a finite universe. We see ourselves inside a cosmic horizon whose radius is equal to the age of the universe times the speed of light. This is, I want to emphasize, this is a local effect. This is a lot like the horizon we see on the surface of the Earth. No matter where you are on the Earth, you see yourself sitting at the center of a circular horizon that's caused by the curvature of the Earth, and two different observers see themselves at the centers of two different horizons, which may or may not overlap. The same thing happens in cosmology, is that two different observers see themselves at the centers of circular horizons, which may or may not overlap. Every observer sees the same thing. It still obeys the Copernican principle, but in this case, everyone sees themselves at the center of a finite universe whose edge is defined by the moment of the Big Bang. So here is what we really see. This is quantitatively accurate. So this is this is our entire observable universe plotted on a logarithmic scale with the solar system at the center, outward into the Milky Way galaxy and then into the realm of the other galaxies. And the further out we look in space, the further back we see in time. So we can see the entire process in principle, of galaxy formation, the universe cooling and condensing into young galaxies, which then combine into more modern form and so on. So the entire history of the universe is available to us if we can look far enough out with our telescopes. Now, it turns out we can't see all the way back to the Big Bang. There's a boundary there that we can't see beyond. We can see almost to the Big Bang, but not quite. Furthest out we can see using light is when the universe was about 300,000 years old. So here, for example, is a recent picture from the James Webb Space Telescope, where they left the shutter open for about 12 hours and collected light from very, very distant galaxies. And you're seeing back in time to when the universe was only a few 100 million years old. A few 100 million years after the Big Bang. The light from the most distant objects in this picture is coming to us from the very infancy of the universe, when galaxies were first forming. And we're already learning surprising things. There's a lot of evidence now that galaxies form much more quickly than people previously believed, and cosmologists are still working out exactly what this means. But this picture from the JWST really contains the entire history of the universe from an age of a few 100 million years up to today. And if you know how to read this image correctly, you can spread that history out and observe it as it happened. So this is a tremendous thing. We don't have to speculate about what the early universe was like. We can see it. This moment, when the universe was at a temperature of about 1,000 Kelvin, about 380,000 years after the Big Bang, was special. This is about as far out as we can see with light for a very particular reason, which is that this is the moment, as the universe cooled, this is the moment when neutral atoms first formed. So prior to an age of about 380,000 years, the universe was so hot, the gas, the hydrogen and helium in the universe was heated to such a high temperature that in fact, all the electrons were stripped off the atoms, creating what's called an ionized gas. And so the early universe was a soup of free electrons and nuclei at a temperature of thousands of Kelvin. As the universe gradually cooled down below a temperature of about 3,000 Kelvin, these free electrons were captured by the nuclei to form neutral atoms. This is important because the universe, hotter than 3,000 Kelvin, or younger than an age of about 380,000 years, would have been opaque. Because of the presence of the free electrons, the light in the universe would have scattered strongly and been in thermal equilibrium with the gas. But an individual photon was constantly scattering, so the universe would have been full of a glowing fog. You couldn't see very far out in space because the light was scattering so strongly off of the free electrons, like light scattering in a cloud. After recombination, this moment when the universe cooled below 3,000 Kelvin, when those electrons were captured to form neutral atoms, the universe suddenly became transparent. And that light from the Big Bang itself that was trapped inside this cloud was liberated and free to stream through this now transparent space. And this light left over from the Big Bang began to stream in all directions in space. And as the universe cooled, this light cooled as well. The wavelength of the light was stretched. And so what would have been this light at the time it was emitted would have been in optical frequencies. The universe would have been sort of a softly glowing, very hot oven. As the universe expanded, this light cooled, and in the present universe, this light is still present, but it is mostly in the form of microwaves. And this is called the cosmic microwave background, and it is the light left over from the Big Bang. And this is a picture of that light that was taken by the ESA's Planck satellite, showing a picture of the early universe when it was about 380,000 years old. And what you're seeing here is, the way to look at this is, we are sitting at the center of this sphere, and that sphere is the sphere of the sky. We are looking everywhere out in the sky and looking at light that came to us from when the universe was 380,000 years old. And what we see is that light is almost perfectly uniform. It's in thermal equilibrium to 1 part in 100,000. And these tiny little fluctuations in temperature that you see that are color-coded in this plot. So the orange regions are regions that are a little hotter than their surroundings, and the blue regions are regions that are a little cooler. These are the primordial perturbations in the density of the universe. Regions that are a little bit more dense would be a little hotter. Regions that are a little bit less dense would be a little cooler. And what we're seeing here is these 1 part in 100,000 fluctuations that later collapse to form all of the structure in the universe. These are the seeds of galaxy formation that we're actually directly observing in the light that is coming to us from when the universe was a little less than 400,000 years old. This is a total tour de force of modern cosmology. We can actually see the initial conditions that led to galaxy formation. Now, remember that the universe, from the point of view of any observers, imagine being an observer sitting in the universe when these photons were emitted. The universe was only about 400,000 years old. So the size of your observable universe, the horizon at that time, would have only been about 400,000 light years. And projected onto the sky today, that horizon at the time of last scattering is only about 1 degree across, about twice the width of the full moon. So what you're really seeing here is that each of these points on this cosmic microwave background sky was a bunch of completely separate universes. They were causally disconnected from one another. So if you, from the point of view of one of these photons being emitted from this very early time, the universe as seen by that photon would only have been about 400,000 light years in radius. And looking out on the sky today, that's only about 1 degree across. So what we see in this cosmic microwave background, and it's a mystery, is that all of these completely causally separated universes, places where in the entire history of the universe, light would not have had time to travel from one point to another, somehow managed to be in thermal equilibrium exactly the same to about 1 part in 100,000. And the standard Big Bang picture doesn't explain this. You can take it as a boundary condition if you like, but we'd like to come up with an explanation for how the universe became so uniform on scales that were causally disconnected from each other, places that had no ability to communicate in the entire history of the universe. And this brings us to the modern concept of cosmological inflation. What does this mean? Inflation, in a sense, is a theory of what happened before the moment of the Big Bang, before that initial singularity when this hot thermal equilibrium universe came into being. Inflation is a theory for the universe prior to that. So we take away that initial singularity, this point at which our laws of physics break down, and we put a model before it. And this model is governed by the physics of vacuum. The physics of the inflationary universe would be very different than this hot, dense thermal equilibrium soup of matter that happened in the early Big Bang universe. The universe of inflation was cold and empty, filled with nothing but vacuum energy at a temperature of almost absolute zero that would have been expanding exponentially quickly because of the domination by vacuum energy. Inflation has a property that it expands so quickly that the universe is expanding incredibly rapidly at an exponential rate. But the horizon size, the edge of your observable universe, stays almost constant. This means that two observers that start out inside each other's cosmic horizon, because of this rapid expansion, would rapidly be stretched outwards so that the one observer would lie outside the other observer's observable universe. This is how inflation explains the homogeneity of the cosmic microwave background, because if these 2 points that later on were outside each other's observable universe would have started out inside within each other's observable universe, so they could talk to each other, reach thermal equilibrium, and then inflation stretches these things out to extraordinarily large scales. So inflation explains this curious homogeneity of the universe on scales larger than our cosmic horizon by saying that an initial small patch is stretched out to scales the size of our observable universe today. So the observable universe during inflation would have been about the size of a grapefruit, and all of the space that was initially inside that grapefruit-sized region of space is stretched out by inflation to a volume comparable to the size of our observable universe today, a ball with a radius of about 40 billion light years. All of that material all of that space during inflation would have been scrunched into a space about the size of a grapefruit. Inflation also explains why the universe appears so close to geometrically flat. So if we start out with a lot of curvature of space as that space gets expanded, just like if we were standing on the surface of a very small sphere, if we make that sphere really big, our horizon but keep our horizon the same, our little patch of it looks flatter and flatter and flatter because of this inflationary expansion. Inflation also does another neat trick, which is something that's very much akin to the Hawking radiation of black holes, where black holes are not perfectly black. They actually radiate a little bit because of quantum effects, because of virtual particles being created out of the vacuum. And some of those virtual particles escape to infinity. A similar effect happens during inflationary expansion, where small quantum mechanical fluctuations, because of the Heisenberg uncertainty principle, because of quantum mechanical uncertainty, empty space is not perfectly empty, but seethes with a soup of these tiny little ghostly particles that are blinking into and out of existence because of quantum mechanical uncertainty. In inflationary expansion, the expansion is so rapid that two virtual particles that pop out of the vacuum and normally would re-annihilate and re-enter and disappear, the expansion of the universe is so fast that these particles get stretched out to outside each other's cosmic horizon and become stuck in the space. They get frozen in the space itself. And this is a mechanism that actually generates the primordial density perturbations in the universe. Those 1 part in 100,000 fluctuations that you see in the cosmic microwave background in the inflationary picture actually have their origin as quantum virtual particles in the empty space of inflation that are stretched out and frozen in a process that is essentially similar to Hawking radiation from black holes. This means I can write down a particular model for inflation, some Lagrangian of particle physics, some theory, particular particle physics theory, and I can actually calculate what these fluctuations that we see in the cosmic microwave background should look like. Inflation is a predictive theory. We can actually predict the form of these perturbations in the early universe that we observe in the light left over from the Big Bang itself. And inflation makes very quantitative and specific predictions that match exactly what we see in the later universe. And for this reason, it's an actual scientific theory. We're not just doing philosophy here. We actually have testable predictions from inflation that we can go out and look at. And inflation, in fact, actually makes these predictions incredibly accurately. So this is a really remarkable thing. By taking this period of early vacuum-dominated expansion where the universe expands by a many orders of magnitude, takes a ball of space about the size of a grapefruit and stretches it out in a trillionth of a trillionth of a trillionth of a second to a size comparable to the size of our observable universe today, carrying with it these tiny little quantum fluctuations, we can actually explain the initial conditions, why the universe is so big, why it's so close to geometrically flat, why it's so homogeneous. All of these things come about as consequences of this theory of inflation that we can implement in models of particle physics and perform quantitative work with. So inflation explains quantitatively and in detail this pattern of fluctuations we see in the cosmic microwave background today, it's a remarkably successful theory and has been tested to really high accuracy by modern cosmological observations. So inflation basically works by saying that the universe starts out with having a bunch of being dominated by the energy of empty space. So you can think of it as a ball rolling down a hill. When the ball's at the top of the hill, empty space has lots and lots of energy to it, and the expansion of the universe is driven at an extraordinarily high rate. But then inflation ends, this ball rolls off the hill, and that energy that used to be in empty space is converted into all the particles of the standard model. And when the ball rolls off from the top of the hill down to the bottom, that potential energy that it had at the top of the hill is transformed into the energy of all of these particles that then heats the universe up and creates these hot initial conditions for the Big Bang. Interestingly, when you look at this process in detail, what you find is that if you fill a universe with this vacuum energy, that this ball, as it rolls off the hill, only does so locally. Most of the space of the universe, the ball stays up on top of the hill. So what you get in an inflationary picture, remarkably enough, is not a single universe like ours, in which the ball has rolled down to the bottom of the hill and filled the universe with a hot soup of particles. But you get many of these bubbles, so that the universe that you get out of this inflationary picture is enters a phase of what's called eternal self-reproduction, or an inflationary multiverse, where most of the space continues to inflate. The ball is still up on top of the hill, driving this incredibly rapid expansion. And only locally does it drop down to the bottom of the hill and creates a universe that looks like ours inside of a little bubble. And this is happening repeatedly. So this inflationary picture of the universe naturally creates this situation where you're creating more and more bubble universes, which are expanding apart from each other faster than the speed of light, creating still more bubble universes. And this process goes on infinitely into the future. So inflation does not just generate one universe, it generates an infinity of universes. Except that inside each of these bubbles, we live in this bubble, and if you plot the formation of one of these bubbles in time and space, so if you look at a bubble that is expanding outward at the speed of light, if you plot time on the vertical and space on the horizontal, that expanding bubble spreads out a cone in time and space. And because of the malleable nature of space and time and relativity, we can borrow some of that time and turn it into space. So an observer on the outside sitting in this inflating bulk would see as a finite bubble expanding outward. From the inside of it, we actually see an infinite universe. And the bubble wall is not a boundary in space, but it's actually a boundary in time. The wall of the bubble lies everywhere in our past, and we live inside an infinite universe that is tucked inside this bubble by borrowing time and turning it into space. So we can never travel to any of these other bubble universes. Our universe, we live inside a single infinite universe. And the reason we can't travel to another universe is not because the boundary of that bubble is some distant boundary in space, but because of the fact that the boundary of our bubble actually lies in our past. And we cannot, without being able to travel backward in time, we cannot travel outside of our own bubble. So we are forever cut off from all of these other universes by fundamental limits of causality. So we live in a single bubble universe that inflation tells us should be one of an infinite number of other bubble universes, each of them forever cut off from their siblings by inescapable laws of causality. And in this way, we have time moving forward in space inside this bubble in this way. And we have, in a way, realized a fundamentally a Copernican universe, one that is reminiscent of Giordano Bruno's infinity of worlds, except that now, instead of an infinity of worlds, we have an infinity of universes. And I like to think that Bruno himself would have found this to be very satisfying. So the inflationary multiverse is a way for which not only is our planet not ordinary, but our universe itself is not ordinary and one of an infinity of others like it. And this is a grand realization of Copernicus's idea of an or Bruno's idea of an infinity of worlds. So with that, I think I will end and take questions from the audience.
So first of all, Will, thank you so much. It was such a nice, such beautiful to follow, especially with no equation and beautiful picture that I think everybody could follow your talk. We have already one raised hand, but before I will go to them, I would like to say that after your talk, of course, it comes me in mind a song which has been written 23 years ago by Red Hot Chili Peppers, the Parallel Universe. I may have to listen to the song again. I checked right now that 23 years ago with this Parallel Universe song. But anyway, so William Wall is asking a question, and please,
sure.
Can you unmute him? Yeah.
Hello.
Yes, you're unmuted.
Hi. Yeah. Thanks. Enjoyed your talk. You have a lot of analogies. I just love those analogies. They really illustrative, I thought. But they lead to a question for me. When you talk about the universe expanding and it's sort of like being on the surface of the Earth and you're looking at your local horizon and it looks flat. And as the Earth gets larger, then you say that, well, it looks flatter and flatter. What then is and our universe looks like it's flat, but I mean, what is the large scale curvature of the universe? What are the large scale properties of the universe beyond that? Or is there any way we can find out?
Outside of our horizon, probably not, right? So it represents a fundamental limit to how far out we can see. And one of the things is that a basic prediction of inflation is that the universe should be incredibly close to geometrically flat. And that we measure that by measuring essentially triangles, right? So if you can draw a really big triangle in the universe, then if the universe is geometrically flat, the angles of that triangle will add up to 180 degrees. If it's positively curved, like if you drew a triangle on the surface of the Earth and it was big enough, you would find that if you added up all the angles in the corners, they would be more than 180 degrees because of the curvature, right? So if we could draw one of these big triangles in the universe, we could actually measure the geometry and measure whether or not it was positively or negatively curved or flat, whether it was Euclidean. We've done that. And in particular, we do that by looking at these little, the perturbations in the cosmic microwave background. So let me actually back up to that slide and explain how this works, which is that if we look at here, the cosmic microwave background, you notice that these circles are the size of the observable universe at the time the light was emitted. And you notice that that's about the size of these blobs. And there's a reason for that, right? Because these blobs are caused by sound waves moving through the primordial plasma. So these sound waves can't propagate larger than basically inside that circle. And so these blobs have a characteristic size. So we can actually, by measuring the size of those hotspots, we can measure the apparent angular size of the horizon at the time of last scattering when this light was emitted. And by looking at that apparent angular size and knowing how much it's been redshifted, we can actually measure the angles of a triangle. So if the universe had a closed geometry, those patches would look bigger in the sky than they do. And if the universe had an open geometry, the patches would look smaller in the sky than they do. So by looking at the characteristic size of these hotspots in the CMB, we can measure the curvature accurate to within a fraction of a percent. And this is done, and the universe is almost exactly geometrically flat, which is a real triumph for the inflationary picture because it predicts this geometric flatness. So I hope, does that answer your question?
Yeah, it does more or less. When I still wonder about the large scale. If the large scale absolutely has to be flat, I mean, beyond the
yeah, outside our horizon, we have no way of telling. We can put limits on that radius of curvature, and we know that it has to be much, much, much larger than our observable universe. But beyond that, there's fundamentally no way to tell.
Yeah, okay. I was also wondering about these universes, the other universes that are out there and that we can't see them. Couldn't you have those cones actually close to each other and they intersect each other over time?
Here.
Yeah, exactly.
Is this what you're looking at? No,
Yeah.
see, what you have is that this basically what we would call a spatial surface in our universe is a hyperbola that's nestled inside that cone, so it never intersects it, right? So it goes off to infinity in that way. And then time moving forward is just nesting successive hyperbolas inside that cone. So in fact, the edge of that bubble is everywhere in our universe, is everywhere in our past. This takes a certain amount of imagination to visualize, I realize.
So we have more raised hands. Now it's Hans Zinecker.
Can you hear me?
Now we can hear you, yes.
Okay. Yes, I can hear you.
I have a question about matter and antimatter. I mean,
sure.
At what time did matter and antimatter split? And if I may add another question, I mean, you have shown these nice expanding boxes of space, but time, and so space is more easily imaginable than time, because time has to be measured by a clock or something. What is the natural clock to measure time?
The natural clock to measure time in the expanding universe is basically the temperature, right? So as the universe expands, it cools. So one clock that you can have to measure cosmic expansion is just the temperature. And in particular, like on this plot that I'm showing here, I have time on the horizontal and I have temperature on the vertical. So as the universe is younger, it's hotter. And our universe today is a temperature of about 3 Kelvin. So we can tell how much it's expanded, for example, since the time of recombination, because we know that the universe was a temperature of 3000 Kelvin then. So we know that it's expanded since then by a factor of about 1100 is the actual number, right? So the temperature of the universe tells us the amount of expansion. To your question of when matter and antimatter separated out, there are 2 answers to this one. A simple one, which is that, for example, electrons and positrons, the antimatter partner of the electron, for example, annihilated with the electrons when the universe was about a second old. So prior to 1 second, the universe would have been full of electrons and antimatter electrons called positrons. They would have been present in the universe in about equal numbers. And as the universe cooled, that matter and antimatter annihilated each other and turned into photons, right? And that was one of the things that contributed to this light that later on formed the Big Bang, was the light that was emitted by the annihilation of matter and antimatter. Interestingly, however, there was not an equal amount of matter and antimatter in the early universe. There was a tiny little bit more matter, about 1 part in a billion. So when all that matter and antimatter annihilated, it left over about 1 part in a billion of this matter. So there's an asymmetry between the matter and antimatter, a little bit more matter than there was antimatter. And we don't understand what created that asymmetry. It happened somewhere, that imbalance between matter and antimatter in the universe happened at some earlier epoch. And there are many theories for how this happened, but we still don't understand exactly what was the origin of this asymmetry between matter and antimatter. But if it weren't there, we wouldn't be here, because all that matter and antimatter in the early universe would have annihilated and turned into photons, and there would have been none of it left. And the universe would just have been full of radiation with no leftover matter at all. So that extra 1 part in a billion is really crucial for our existence.
So this is not explained by inflation?
No. Inflation itself does not explain this, although there are inflationary theories which create matter-antimatter asymmetries as part of the inflationary process. That's an add-on. It's not intrinsic to inflation itself.
So we have 3 more raised hands. Let's go on, that everybody has a possibility to ask questions. The next one is Andreas Kaling, then John Cooper, and afterwards Annie Robin. So please, Andreas.
Yes, hello. Before today, and before your talk, I thought I understood that the time and space were created together. But now I learned that there was a vacuum, an infinite vacuum before the Big Bang, in which particles popped in and pop out. And so there was time before that Big Bang even. What am I?
Yeah, the universe, the inflationary universe could be vastly older, right? than that 13.8 billion years, trillions of years, quadrillions of years. It could be. Interestingly enough, however, you can show mathematically, there's a theorem called the Borde-Guth-Vilenkin theorem, which was proven by the three gentlemen with those names, that show that even that inflationary epoch, that could be unimaginably old, that also had to have a beginning. And so you don't get rid of the beginning of the universe by introducing inflation, but what you do is you push it off into some unimaginably distant past where the universe, we have no idea what the properties of the universe were that led to the inflationary epoch. It's completely unknown.
Thank you very much.
Next question is from John Cooper.
Hello, John.
Hello, can you hear me?
Hi.
I can hear you.
Okay, well, in this simple picture where, you know, everything stands at the speed of light and the speed of light is constant and so forth, where would you put singularities like black holes and Einstein, those are bridges and so forth into your pictures?
Well, I mean, in the standard Big Bang model, that moment of the Big Bang would have been a singularity of a slightly different sort, since it's spatially infinite, right? So that it would be a singularity that would be at a time-like boundary. But of course, in this picture of the history of the universe, then these black holes would have formed at some point in the very early universe, like certainly after, you know, when stars end their lives and form black holes, then you have these late-time singularities that are captured inside the horizons of black holes as well. So perhaps I don't understand the question completely, but those singularities, like black hole singularities, for example, arise later on in the history of the universe. Am I answering your question, or am I getting a misunderstanding it?
So we have one more question. It's from Annie Robin.
Hello.
Yeah, Annie.
Yes, I have something, a very naive question. I am not, I don't know much about cosmology, but after Anne's question about the disequilibrium between matter and antimatter, would it be possible that there is some fluctuation from one universe to the other, as you said that there were many universes in parallel? And so we can imagine that from a quantum fluctuation in in our universe, there is a small difference that makes matter exist now. And in other universe, the disequilibrium is different and there may be antimatter or maybe nothing.
That's entirely possible. We really don't know. But that one possibility for that is that that's right, that essentially that baryon asymmetry is a random thing that varies from universe to universe, and other versions of this bubble universe might have slightly different matter and antimatter asymmetries. That's an absolute possibility. Yes.
So there are two more questions. Let's see if these are quick questions. One is from Karim. Please introduce also yourself, perhaps.
Did you hear me?
Yes. Yes, I can hear you.
Thank you for your talk. A very quick question. So could you comment on the speed of the inflation? At some point you said it's very faster than speed of light.
Yeah, so here's the thing. In relativity, in Einstein's general theory of relativity, two points in this expanding space are actually can move away from each other faster than the speed of light. So when you think about it in terms of the observable universe, our horizon, an observer outside of our horizon, another way to think of the fact that we can't see them, right, outside of our observable universe, is that they're moving away from us faster than the speed of light. So in the case of inflation, if we look, so if we have, let me bring up this, if we have two observers that are inside each other's horizon early on in inflation, they will be moving away from each other at less than the speed of light. But then later on, inflation happens so rapidly that these two observers that started out moving away from each other at less than the speed of light will be moving away from each other faster than light. And so, and this is perfectly allowed within general relativity, as it turns out.
Okay, thanks.
So let's have the last question from Alphonse Sterling. I think he's also from Buffalo, if I am not mistaken.
No, I'm not. I'm in Huntsville, Alabama.
Oh, sorry.
Yeah, no, it's okay. Yeah, I didn't quite get the conservation of energy. How is it conserved with the vacuum energy during the expansion?
Well, the short answer is it's not. You're actually creating energy out of nothing because you're creating more empty space, and the empty space itself has energy. So this directly violates the usual concept of conservation of energy. You're literally creating energy out of nothing. This is also a loophole in Einstein's theory of relativity. Einstein's theory retains a concept of energy conservation called local energy conservation, which is that energy flowing across the boundary of that box has to add up, so that the energy flowing into the box from the outside has to match the energy flowing that is lost by the environment, or vice versa, right? So that the total amount of energy flowing across the boundary has to add up to 0. But you can create energy out of nothing inside the box as long as it doesn't flow across the boundary. So this is a very strange loophole in relativity, so that you can violate conservation of energy in this way. So expanding universes violate conservation of energy intrinsically is the answer to that.
So yeah, I would like to thank you once more.
Thank you very much. These are some great questions. I really appreciated the
thank
questions.
Thank you to all of you for the questions, and thank you again for having accepted our invitation for this great talk. And I would like to announce already the next talk, which will be on the September 22nd. And it will be about cosmic neutrino, a background, by Julien Lescourgeuse. So I'm looking forward to see all of you again next Thursday for the next talk on captivating cosmology on our Game Changer seminar series. Thank you once more, and have a nice, in your case, day, and for the European, a nice evening.
Thanks very much.